Good evening, everyone. My name is Ranjita. Welcome to week 11 live interactive session for Advanced Computer Networks course. Yeah, my name is Ranjita and I'm a PhD scholar from Department of Computer Science and Engineering, IIT Hyderabad. So we'll discuss first the topics covered in the previous week, week 11, and we'll take a look at the questions. So even though in the topics, quick and green data centers were covered, I think the questions were majorly from the content distribution and information-centric networking. So we'll quickly take a look at quick, what quick is, and then move to CDN. Yeah, can you just confirm if the screen is visible and if you can hear me? Okay, thank you. All right, I'll share the writing screen. Give me a minute. All right. So we'll just take a quick look at what quick is. QUIC. Okay. Uh, So we know we have already seen in the previous classes that in the TCP/IP model, in our TCP/IP model, we have the protocol stacks, right? We have the physical layer, we have the link layer, we have IP layer, we have transport, on top we have application. So we have also seen that the transport protocol, majority of the applications run over TCP. So we have majorly two transport protocol, TCP and UDP, and majority of the internet applications were running on TCP. So the major properties of when we learn about networking, this is something that at the transport layer we learn what is UDP, what is TCP, and in what way they both are different. So TCP is actually a reliable transport. So it ensures flow control. That is, one can control the traffic flow, then ensures order delivery of packets. There is something called sequence number in TCP, using which at the receiver, on receiving the packets, the TCP will buffer it and make sure that when it give it back to the application, the packets are ordered. So, for example, I'm sending out a packet with the sequence number 1, 2, 3, 4. It's a large chunk of data which is split into four packets, four TCP packets. Okay. On at the receiver end, receiver, if suppose over the internet, if 2 is received first, followed by 1. So 2 and 3 is received, followed by 4 and 1. TCP will buffer and it will reorder it in this form, and then it will be delivered to the application. So TCP takes care of order delivery of packets. And also TCP have this congestion control mechanism. So when the packets are not getting delivered, so TCP have this acknowledgement mechanism, right? So basically a packet is sent and the receiver, so this is the sender, this is the receiver. And the sender will wait for an acknowledgement. This is data and the ACK. So sequence number plus length of the packet gives the ACK number, right? So if the sequence number for this packet is 1 and this is a 20 byte packet, the sender will expect an ACK with 21. On receiving the ACK, it will send out the other packet with sequence number is 21. So this is how, and then it will, if it is again a 30 byte packet, then the expected ACK will be 51. The ACK with acknowledgement will be expected with acknowledgement number as 21 plus size of the packet, which is 30. So when an ACK is received, okay, there was no issue in the network. The reception of an ACK tells that the packet have been delivered properly. Okay, so that's how TCP ensures reliable transport. So okay. So, with this reliable transport, so to ensure this reliability, I've told you that there is the sequence number and all that. So, before starting the data transfer with a certain sequence number, first TCP have this something called as the famous three-way handshake. First, when I'm trying to connect to a particular server, or when I'm trying to get some data, or I'm trying to access some website, if it is running on top of TCP, first I'll be the client and the server, the from where I'm going to where I'm going to connect will be the server. And the first thing that will happen in TCP is a establishment of a connection. So a connection establishment will happen first, and it happens using something called as a three-way handshake. So when a sender and a receiver wants to communicate over TCP, first the sender will send a SYN packet, receiver will send a SYN plus ACK, that is ACK for the SYN and another SYN in this reverse direction. Yeah. And then sender will send a ACK for the SYN received. So basically, with the SYNAC, the sequence number and all gets set. So in the SYN, it will tell what will be the sequence number that the sender will use. And in this SYN, the receiver will tell what will be the sequence number it will be using for the data transfer. So once the connection establishment happens, then data transfer happens. And the ACKs will also come accordingly. Okay, but this three-way handshake actually though the sender is ready to send traffic here, it actually starts sending from here only. Okay, so there is an amount of time that one waits before it actually start to send traffic. So this is called the connection establishment. Until the connection is established, packets cannot be sent. This is for a simple TCP. So the web traffics that we normally use in our browsers are and our is typically a HTTPS, which uses TLS, transport layer security. So this TLS works on top of TCP. So TCP will have its three-way handshake. In addition to that, so when TLS comes into picture, TCP's three-way handshake will be there. In addition to that, TLS is for security purpose. So all the encryption, authentication keys have to be established again between the client and the server, or the sender and the receiver. So TLS will have its hello, client hello, server hello, and then client finish, server finish, and some exchanges again going on for the, this is the TCP. Okay, this is SYN, ACK, ACK. Then on top of that, TLS will have a client hello, followed by a server hello, and then a client finish. So by the time one can, so this is for the TCP and this is for the TLS. So even though the sender is ready to send the traffic, it is only from here that actually it starts to send the packet. So there are a lot of time actually goes off in this connection establishment. This is one thing. Another thing is, as I have just told you, TCP takes care of this in order delivery, right? So nowadays in a web browser, there are lot of objects that when I'm trying to access a web page, it consists of lot of objects that needs to be loaded. Okay, and all of these objects actually comes as different streams, but due to this in order delivery of TCP, there is a problem called head of line blocking. It actually causes a head of line blocking, due to which the web page loading actually gets delayed and the user experience gets affected. So how that happens is, for example, we know, right, typical web pages contains tens of hundreds of objects. Okay, and the browser could render partial pages with the objects that finish downloading to provide a better user experience. Okay, so when we have TCP connections with streams with single TCP connections, this problem of head of line blocking occurs. That is, for example, I we have received one, packet two in order, and then packet four. Okay, packet 3 is delayed, but this packet 3 which was delayed, this 1, 2 and 4 corresponds to same object 1, whereas the delayed packet 3 is actually corresponding to object 2. So even if this packet 3 is not received, ideally this 1, 2 and 4 can be delivered to the application, so that that object could have been made visible to the rendered and made visible to the user. But due to this uh, in order the delivery of TCP, this head of line blocking issue occurs at the client side, and this actually impact the user experience. Okay, so this is one issue. Another issue is the time it takes to kickstart the session. So with all this difficulty, these people came up with a protocol called a Quick, which is run on top of UDP. And what they have done is they use the simple UDP doesn't have any connection establishment mechanism. If you want to send a packet, just send it off. That's all. And it doesn't provide any reliability either. So these reliable aspects that is required is now built in the application layer. Earlier it was taken care at the transport layer, but now we use a simple quick UDP mechanism at the transport layer, and this in order delivery, the reliability aspects of all that is taken care in by the at the application layer, by the application. Okay, so that is the major. I'm not getting into the technical aspects in quick how they solve this head of blind blocking is by like having stream specific offsets instead of having a single offset across sequence number across the whole page. It's stream specific. So if 1, 2 and 4 is delivered, that gets that particular object gets rendered. So because of this, the head of line blocking issue is solved. I mean, it's an RFC, it's a typical protocol mechanism is there. I'm not just getting into those details, just to make you understand. With quick, since we move all this to application, what will happen is the data transfer starts now. On top of this quick, TLS is also provided, security is also provided. Okay, then so there is kind of there is no RTTs that is getting wasted due to the connection establishment phase. We immediately start with the request, then we get the response, HTTP response also. So it's like a zero RTT kind of. Okay, so it just the underlying transfer protocol is changed to UDP, and whatever functionality was needed is now whatever functionalities of TCP was required, like reliable delivery and all, is now moved into the application space. So Google Chrome, if you are using the browser, we actually underlying it uses quick protocol. Okay, so that is just a quick brief on quick. Now let's go to content delivery network CD. So let's first look at content distribution. IP networks. So earlier, when the internet was designed, the kind of content that we have on the internet was not something this was designed for. It was majorly for email, file transfer kind of applications. But today we have rich multimedia content explosion in the internet, right? So normally in the internet, it's a point-to-point communication, right? When I'm communicating with a server, I mean, like we type in the URL, the URL gets transferred to the IP address. If I'm just accessing the Google search engine, in the browser, we go and type www.google.co.in, right? So that URL gets translated to the IP address, and then I get the web page, right? Mhm. That is the like kind of a point-to-point communication is what it was designed for. But today, even this example that I'm telling is actually not a similar way, right? It's multi-point distributed. So earlier, if we have had only one server for a particular application in a particular place in this whole world, now it is not the same. So when I am accessing the Google search engine, it actually redirects me to the nearest server that Google have kept. So on the world map, there will be multiple such, we call it as point of presence for each of these giants like Google, Microsoft, and all. They have their point of presence in different locations in the world. And when we are accessing from India, it might take us to maybe server in Bombay, or maybe server in Singapore, or something like that. But earlier days, it was not designed in this form. But today, it is all multi-point distribution. Okay. So let's take a simple, I mean, in the normal scenario in the IP network world, for example, there is a YouTube. When we are streaming from the YouTube, so there is this YouTube server available, and multiple people are accessing it, right? Host 1, host 2, host 3, host 4. if even if all of us are accessing the same content in the earlier single point to point mechanism, it will be like H1 access the original server, it will access it, it will get the content. Here again, access, get the content, access, get the content, access, get the content. Right? It could be the same content also, that all the four of them is accessing. And if suppose internally, if it was like that, like we had a server and probably there was it goes via multiple routers, and here we have H3 and H4, and maybe here we have another two routers, and then we have H1 and H2. So whatever content, when H1 requested, it went like this and it came like this, right? And when H2 requested, the same content actually traversed the similar path, right? Same way with H3 and H4. An ideal scenario could be that when the YouTube is giving the content, probably this router can keep the content, this router can keep the content, this router can keep the content. So when H1 requested, if it is like this, if the routers are keeping the content, the request R1, R2, R3, R4, like R1, R2, and R3 had the content. So now when H2 is requesting, it goes to R2, right? R2 already have it, so it doesn't need to go all the way, and the same content need not traverse via R1 and R2 again. R2 can directly get it, R4 can have it, and then it goes to H2. Same way, if it was like yeah, if H3 requested a content, and then when it was delivering the content, it is stored in R1 and R5. Then when H4 requests, directly R5 can deliver the content. It doesn't have to go all the way through the same path. So this is the ideal scenario. So whenever the routers are delivering the content, look them up and cache it, so that when the next time the request come, the router can give it by itself. This is the ideal or better distribution scenario, right? But like how can the router know this is going I mean, this is the content that the previous user accessed, this is the one that the new user is asking for, which content I must cache, how long I should cache, this is the most popular one to cache. So those are like the challenges that are typical when we think of the information centric network, one need to see. But even in the normal IP networking also, there are certain ways we are actually achieving content delivery. Okay, so currently it is happening, right? We are accessing YouTube, we are accessing Netflix, Amazon Prime, and whatnot, n number of different streaming channels we have, Hotstar, this, that. So we are accessing YouTube contents, we are accessing contents from the network, and it is not that these contents are delivered from a single source. So it is happening, content delivery is happening over the uh, network, current IP network. So what are the mechanisms that majorly help uh, optimize the content delivery in IP network? Is one is via web caching, another is multicasting, and next one is CDNs, content delivery networks. Okay, so let's see what this web caching is. Okay, so web caching, the scenario is majorly done with like and at an enterprise level, one does some amount of caching. That is what web caching is. So for example, if we take institute like IIT Hyderabad, or in any other, for that matter, any other institute. We have this main server, for example, this is the server to which the request is going. And within the enterprise, there is something called cache servers. For example, another one host H1, H2, H3. For example, if we take the example of a college, if a student have requested a particular YouTube video of maybe a very popular song, this will go here, then it will go to the main server, it will come back. Right. So the cache server will cache this content. So at a later point, if a second student requests the same content, then this cache will send it, respond back. It will it is already having it cached. So the request does not have to go all the way to the original server and come back. So that is how web caching works. So it's done in the intermediary at an enterprise level. So there are mechanisms to ensure that the cache is always up to date. And when lot of requests are being like done, what to cache, what not to cache, those mechanisms are all in place. And sometimes there might be an updated content in the server. How does the cache server know that there is an updation in the server? The content have been updated, so there is a mechanism to get that done. So this is one example of content delivery optimization in IP network. So enterprises normally does this. Okay. Next is another one is the multicasting. So till now we have seen we have seen IP addresses, and we have seen that the how the packets are routed. So the those were examples of unicasting. So there is a source IP and there is a destination IP, and this destination IP belongs to a single host. Okay, so it's from one host to another host. It is a unicast. Where multicast means that the source will be the same, single source, multiple destinations. So this it doesn't mean multiple destination IP addresses. There will be a single there will be a source IP. There is a destination IP. But using this destination IP, multiple sources will receive the packet. So how multicasting works is there is this concept of groups. Okay. So for example. Let us assume that there is this particular new channel or that have started and people have subscribed to that channel. So the only those who have subscribed to that channel need to get the data, right? So how we can kind of visualize this is there will be multiple groups like G1, G2. And yeah, G1, G2, G3, etc. And different people can subscribe to it or join the group. Join the group. Okay. So this G1 will have one IP address like 224 dot, which will be in the multicast range x dot some one. It is as okay. This could be G2 will have another IP address like that. So whoever have subscribed or joined G1 will get all the packets sent to this particular IP address. Whoever have joined G2 will get all the packets that have been sent to this particular IP address, multicast IP address. So the concept is, for example, we have some routers here. Mm, Okay. So this is okay. So H1 and H2 have, let's assume that H1 and H2 are member join the G1, and H3 and H4 have joined G2. Okay. So now, in a normal scenario, when H1 is asking for a content which belongs to that particular group, what will happen is from this is the server, it will come to H1. Now, when H2 is asking, it will also come all the way to H2. Okay, so with multicasting, what will happen is H1 and H2 have joined this group, right? So when for a particular group, when we want to send some data that needs to reach to all the members of the group, what happens is it is not that it will be sent to H1 and then H2. No, it will be just sent once. It will go to H1 and H2. So let me make it more clear. So in the earlier scenario, we had once it was sent to H1 and then another time it was sent to H2. So there is this traversal happening twice. Whereas with multicasting, how it will happen is both H1 and H2 have joined the group. So from the server will send the packet to the multicast IP address. It will be sending the packet destination IP will be the multicast IP 24.x.x.1. And so this routers will know how like when I tell join the group and all these multicast like unicast routing multicast routing tables will be there in the routers, and those tables gets updated. Okay, so when a packet for destination 224.x.x.1 comes here, this router would have already learned that okay, I need to send it here, so that it will come once here. And then this router will have already learned that H1 and H2, which is reachable via R1 and R2, are members of the group. So it will send one here and one here, and then it will reach here. So you can see that there is no replication done here. Here we were sending it all the way from the server once to here, and then all the way from the server to here. So this part, it was actually replication. Right. So, but here there is no the single once we will send and it will reach all the people who have subscribed to that particular group or who have joined that group. So, this is another way of how we have optimized the content delivery in IP networks using IP multicasting. Instead of sending to n people individually, these people who are of interest groups, group IP is formed or multicast IP will be there, and when we send it to the multicast IP, it will reach all the corresponding hosts. So multicast routing protocols are there which will take care of learning these group membership information and populating the routing table with these information. Okay, like how we have the normal routing protocol like RIP, ISPF, BGP. There is multicast routing protocols like PIM, DVMRP, and all that. So they learn this. There is IGMP also, Internet Group Management Protocol. So the main mechanism is joining the group, leaving the group. Some control messages will be there. From these, the routers will learn, okay, there is a member here, there's a member here for this group. Like that, it will learn. And when packet comes for that particular multicast IP address, routers takes care of forwarding it. So this multicasting was another optimization. Next one is content delivery network CDN. Next optimization is CDN, which is okay. Yeah. So in content delivery network, what we do is like I've been telling, right? In multiple times we have taken this example. There is these uh, like the most common application and content providers have what is called as multiple servers located in different parts of the world. They call them as point of presence. So assume that if we have only the YouTube server running all the way in United States, how long it would take for us to buffer the YouTube video and stream it and watch it? It's like the propagation delay from India to US itself is in the order of milliseconds, right? So it will be the user experience would be pretty bad in that scenario, and it has to travel a long distance, and the multimedia contents are large in size. So it will be very, very, very slow. So in with CDN, instead of one server in the whole world and giving it to everybody, streaming it to everyone, what it is done is there will be a central server. In addition to that, as I said, there are multiple servers also kept in various parts of the world. And when a particular request comes, for example, from India, when we are trying to stream some YouTube video, I don't know where the CDN is. I'm not sure if it is in India itself or Singapore. So, should have checked that. Okay. So whichever is nearer, closer to us, that particular, so these are the content servers. Okay. So whichever is closer, that particular server will respond back. Instead of all of these requests going here, it is now taken care. This is not happening. Right. The nearest server is here, the nearest one is here, the nearest content server is delivering the data or the content. So major applications are video streaming and web. Okay. So how it works is typically the the original one actually will not respond to the request at all. So if suppose there is a request going via maybe some routers, and this is the original server, but the nearest point of presence is here. So this request will go here, 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 and he will tell ki, sorry. Mm, yeah. You tell ki, okay, this is the point of presence, you go and get it from that place. So the request will go and then the response will be. Further request will go here and response, request, response. So this is what happens. So the major advantage of CDNs are majorly, okay, of course, time, right? It reduces the response time, right? When a user wants to access it, the response time is largely reduced. And another aspect is redundancy is built, because now there are multiple servers available. Now even if this is gone, and for this host, if this content this server is nearby, it can be served here. It doesn't have to go to the all the way back to the original server. So redundancy is also maintained. And another aspect is, with respect to security, this central, the original server is, none of the requests are actually going to it. It's getting handled by the edge servers. Okay, so this is also secured from malicious request. All those one level of filtering happens at the edge servers actually. Okay, so this is how the current content delivery networks works. Right. And another optimization that is done. This is actually done by the service providers. Like Google takes care of its by itself. Amazon will take care of its thing like that. Okay. Another optimization that we normally see in is the something called a transparent. It's called transparent caching. So this is normally done by the telco operators. Okay, that is it. This is very this caching is actually done very close to the end user. This content um, delivery network that we saw is not that close to the end user, but this is very close to the end user. Typically, on demand based, the telecom operators sometimes do this. What to say? The caching and by telecom operators. For example, like if there is some match going on or some highlights which was very significant in that match, or maybe some very significant happening somewhere in the world, which people think would everybody we will be looking into or streaming in. So those kind of some typical content which people tend to watch again and again, those short clips, those things the telecom operators sometimes tend to cache in their side. So typically, this will be a host, and this will could be a mobile phone. And this is where the telecom operators. Okay. So it will have an aggregator core, and it will have a this is where it will cache. This will be the gateway, and then it connects to the core internet. This is the this is edge, like where our tower will be there, no? The tower area. Then the aggregator. So to some this is the telecom operators area, and then it gets to the internet. Okay, so within their small towards very close to the user, they will do the caching so that one can like users can enjoy it at a very fast rate. So it actually reduces the bandwidth usage also, right, for the telecom operator as well. Then another mechanism is the peer-to-peer. Another mechanism is peer-to-peer networks. Another optimization done on IP for content delivery is peer-to-peer mechanism. Like I think everyone will be aware of this BitTorrent, right? How it might happen. So there will be a lot of users which are connected like via overlay network or something, and their mechanism, like the moment you get a file, you also become a server. As a client, you retrieve, you get the file, you request and you get it. The moment you get it, you also become a server. Then you can whoever is requesting, you can give same way. So everybody who's part of this peer-to-peer networking becomes a both the client and the server. So this is another content delivery optimization done in the current IP networks. Okay, so what are we trying to achieve with this? It is nothing but from an user's perspective, uh, irrespective of what I'm trying to access, I'll be accessing probably image, video, web page, audio, whatever it be. So, how do a user look at a content distribution network? From the user's perspective, whatever I access, it could be an image, it could be an audio, it could be a video, it could be a web page. I'm not bothered about who is providing me, but I need that like fast access, right? Fast access is what we are interested in. I'm not interested. I mean, I actually doesn't even know when I access the Google or YouTube who is serving me, right? Whether it is a server in Singapore, or whether it is something in Bombay, or whether it is somewhere in US. I don't know. Plus, I'm not bothered about also, right? As a user, we are not bothered, or we are not interested in looking at or knowing who is sending it. We are only interested in, okay, I went to Google to see this particular song or video, or this particular NPTEL content or technical lecture or whatever. I wanted this information, I went there. I have to get it at the earliest. That's all what users are interested in. Okay, so when we're trying to uh, design a new network for such content delivery mechanism, so the main highlight or the main objective should be it should enable the delivery of the content, must be efficient, secure, and high availability. It can't happen that we are trying to access a particular video, and like for example, you have an exam tomorrow and you want to learn about the TCP/IP protocol or the UDP protocol, and you got to know that so and so lecture video from that professor is very good, and you're trying to access that video, and if you don't get it due to some issue at the server end, it's not a good user experience, right? So high availability is also equally important whenever user is trying to access the content, and should be able to, it should be available to be provided. So though we have lot of optimizations and content delivery methods, the major limitations is there is no standard way of doing it. Like though we have CDNs, like how we have seen it, right? How the CDNs work. Here, everyone, each provider do it in their own way. There is no standard followed across this thing. Okay. Plus, when the transparent caching comes into picture, these are like controlled by the service providers. So content when this is done, content authentication and protection is also equally important. So one of the major limitation of existing content delivery mechanism is that there are a lot of players involved, and at various places, because there are various places we can do this. A lot of people are involved, and there are no standard as such present. So, in this information centric networking, it's like a approach towards designing a content delivery network. So, maybe designing a new network for information or content. So when we're thinking about like, okay, let's think of designing an information centric network. So where information is the core, like content is the core. I need a content. So now how I can have a network that will deliver the content to the users, irrespective of where it is present, in an efficient manner. So what are the objectives, or what should be the goals of such an information centric network? When we are trying to design a network keeping information at the center, what should be the goal of that particular um, network? Having seen how the currently how we are doing, what are the disadvantages, how one can design an information centric networking. So one thing that we would want to have is delivery efficiency, right? It has to be very efficient, and the content has to be delivery efficiency. That is, content has to be delivered very fast. Then availability and authenticity. And it should be improving the like the number of places where the replicas are to. For example, so looking, I don't know how to put this across. It's a conceptual idea, like so. When we say delivery efficiency, when a user is trying to access content, the user should be able to, like the speed at which I get the YouTube video streamed should be pretty fast, right? The content has to be delivered very fast, and I should be able to access the content regardless of where it is present. Basically, currently in the CDNs, how are we accessing? We are accessing it via the URL. Okay. And how does this URL? Okay, that I think I missed to tell that. So here, how does it work? Is it is via the DNS. Okay. So the DNS is actually kind of updated to ensure that when I search for Google or YouTube, this particular server's IP address will be given to me. So that's how the in the current um, content delivery network it is taken care via DNS. So in this information centric networking, what we are trying to look at is like instead of every content should be having a name, and one should be able to access the content using its name. So it's like name based identification, and then it becomes name based routing. Like in the current IP networking, it's basically IP based, right? We will identify the host based on the IP address, and the routing is done based on that. So in the information centric networking, the goals should be like goals are like one should be able to access the content regardless of the location, and then one should be addressing the content using the name. Routing should happen based on the name, and the data has to be independent of the location, application, and the underlying transportation. So data that I want to, the content that I want, is independent of the location, application, and transportation. I think we can look into some questions and then revisit if it is needed. Right. Go back. We'll go to the previous year's questions and then look into the topics if as and when it comes. Okay, so the first question is, there is nothing much to discuss. It's whatever the faculty have explained since it's a theory class. So I thought, yeah, we'll go to the questions probably. That would be interesting. Okay, the first one is which of the following is incorrect? Which of the following statements is incorrect about CDN? CDN comprises a single centralized server that caches the contents Okay, so can you go through the question and let me know which one is the incorrect statement about CDN? So the question is, which of the following statement is bar are incorrect about CDN? CDN comprises a single centralized server that caches the contents. CDN distributes the contents to end users through a set of CDN servers. CDN prevents servers from becoming overloaded, and CDN is deployed as an overlay network on top of existing network to host the content close to the end users. So, so we have seen, right, CDN, it's actually basically multiple, from a single central server, we are actually distributing the content to multiple servers, right? So CDN is never a single centralized server. There are more than one servers, and we use it so that it will be closer to the end users. So D is correct, A is wrong. Then B is like CDN distributes the content to end users through a set of CDN servers. That is also correct. And it prevents the server from becoming overloaded because now it's distributed, right? So load also gets shared. So A is wrong. B, C, and D is correct. So incorrect is A. So the answer to the question is A. The next question. Which of the following technique is but are commonly used for content delivery optimization in current IP-based network? Are used for content delivery. And the one more CDN. B is transparent caching. C is IP unicasting. D is IP multicasting. What is the answer here? Which of the following techniques are commonly used for content delivery optimization in the current IP-based networks? So we have seen that, yeah, CDN is a way of optimizing the current IP-based network for content delivery. Transparent caching is something telcos do for optimizing content delivery in IP-based networking. Same way, IP multicasting also we have seen. That is also an optimization done in the current IP-based network for content delivery. IP unicasting is nothing, it doesn't add anything to the content delivery. So this is wrong. The rest of the three are correct. So which of the techniques are used for content delivery in IP-based networking? A, B, and D. So these are the three techniques used. Next question. Which of the following is not true? About information centric networking architecture. A, efficient content distribution. Ubiquitous caching. Okay, so which of the following is not true about ICN, information centric networking architecture? So can you read through and answer? Can type in the answer. Yeah, is not true about. So it is efficient content distribution is something that ICN does. Okay, ICN's main goal is efficient. So it is what it is asking is what it's not what ICN does. It is asking what ICN do not do. Okay. So yeah, A and B is something it do. It does the caching everywhere. It want the content to be distributed everywhere, but data has to be independent of the application and the location. So these two are wrong. A comma B is the answer. The next question. Which of the following is a challenge? Is a challenge in deploying ICM. Which of the following is a challenge in deploying ICM? First one, difficulty in securing and protecting data. B, difficulty in caching. Incompatibility with legacy IP-based system. D, inefficient in terms of routing requests. Okay. So which of the following is a major challenge? Is a major challenge. Challenge in deploying ICN. So difficulty in securing and protecting data. Yes, that is a challenge. Difficulty in caching is also a challenge. Inefficient in terms of routing request is also a challenge. But on top of all of that, the biggest challenge is actually its incompatibility with the legacy IP-based system. So in ICN, it's more like a named network, right? What we are looking for is content. Naming has to be based on the content. Routing has to be based on the name. That is the concept that we are looking in with ICN. Whereas in legacy IP-based system, it's not IP-based, right? Unicast IP-based. IP-based systems, IP-based routing, everything. That's how it works. So it's very different the way ICN is being looked at and the way how the legacy IP-based system is not compatible. So incompatibility with the legacy IP-based system is the major challenge when it comes to deployment. When we are foreseeing and when we are designing a new architecture, yes, we can design it in the in whatever way we want. But when it comes to deployment, we know the current internet existing IP-based internet system. This is how it is working. So compatibility with that system is very important when it comes to deployment. So this is the right answer for this particular question. See. Now the next question, following statement is correct. Which all are correct about traditional IP-based content caching technique. A. Transparent caching. Transparent caching scheme, I am writing it as TCS, okay. Usually managed by service providers. TCS. Web caching, two copies of content C are stored servers belonging to different providers. Caching system will access the content using the same URL. Okay. So, okay, transparent caching is something that we have seen that the telcos do it, right? When they expect that okay, this particular piece of content or this portion of the stream data could be on demand. There is a potential chance of this to have high demand. Then they do the caching in locally towards the edge. Okay, so that is what transparent, the operators do that, telco operators do that. That is transparent caching. So, correct about IP-based content caching. Transparent caching schemes do not improve the response time. So, will it improve response time? It's doing a caching, right? So, it does improve the response time. So, the statement is wrong. Then, transparent caching scheme are usually managed by service providers. Dirty. മരുന്ന് കുടിക്കാൻ സമയമായില്ല മരുന്ന് കൊടുക്കുകയല്ലേ അത് പറഞ്ഞു Yeah, sorry. So, right. So, TCFs are usually managed by service provider. So that is correct. Then it can intelligently decide which content can be cached. That is also true. In web caching, if two copies of the content C are cached are stored on servers belonging to different providers, and caching system will access the content using the same URL. This is wrong. So how web caching works is, so we have the enterprise. Within the enterprise we have the web cache. This is the web cache. Okay. So a particular user is accessing, and same content C is provided by this guy and C is provided by server 1 and server 2. Okay, and if the URL is different, so if it goes here, then the caching will be based on S1's URL. And if the request is going here, then the caching will be for S2's URL. So yeah, it won't be same URL, it will be different URL. So this is wrong. Next question. What is the role of forwarding information base in ICA? To store content objects, to store host address, to store the outgoing interface for each non-name prefix. And D, to track the forwarded request. So here the forwarding information based in ICN is not definitely, it's a forwarding information base, right? It's not to store the content nor to store the host address. It is to store the outgoing interface for each name prefix. So it's when you know that okay, this named content can be reached via this particular outgoing interface. That information is will be in our forwarding information base. Like however routing information base have the content same way. This is what will be stored in FIB for ICN. It's not to track the forwarded requests also. So the answer here is C. Major challenges associated with multi-point distribution. In the current scalability, security, mobility, so, the major challenges associated with multi-point distribution in the current architecture is majorly like the scalability, security, and the mobility aspect. Reducing congestion is not a bigger challenge, but these are the major challenges A, B, and C. The next question. How does ICN handle requests for content? Yes. So, how does ICN handle requests for content? So, routing request for specific server based on the requester's IP address. So, in information centric networking, we have seen that here the name, it is based on the content name. We identify the content based on its name, and routing is also based on that content name. Okay, so it's not, so routing request is not based on the requester's IP address. A is not correct. Now, using a content name to locate and retrieve data from any available network node. So, yes, content name is actually used to locate and retrieve the data. That is true. By broadcasting the request to all devices on the network, that is not correct. By sending the request to a specific server based on the content's location. No, it because we have already seen it has to be independent of the location also. So it's completely based on the name of the content. So here B is the answer. Next question, second last, one more is that. So there is this representation like naming scheme, TS flat structure. Oh, right. Okay, so basically here the question is about matching. Okay, so we had the flat addressing and we have hierarchy, how the contents can be named, hierarchical addressing, and we also have attribute based addressing. So here the options are for MP4 2GB quality HTS. Interview. Okay, so let's take a look at the different naming. schemes. Okay. So, naming convention, I see it. So, one must be uniquely identify the content. Okay. So, one should be able to uniquely identify the content. And it has to be persistent. That is, there must be a binding from the with the name. We should be able to identify the content, and one should be able to scale this mechanism. So, if we are choosing a naming method, like we have billions and trillions of contents, we should have should be able to come up with such names, and we should be able to uniquely identify each of those contents. So, we should be able to scalability. Then using this name, one must be able to do the routing. It has to be routing compatible. So there are different types of naming. Okay, one is flat naming. So here flat naming is like you give some unique name to the particular content. So one method is like how can we have unique to the contents, like when how do we ensure the it is unique, scaling issue will come, right? So to address the scaling issue and to have this unique naming, what have been thought is like do a hash on the content and then append the name. Okay, so when somebody is trying to access the content with the name, one need to search all the content which have that name, and then the hash has to be cross-checked. So for flat naming, the hash of the content is used plus the name is used. So that is with respect to flat naming. The other naming is so what happens is we will have a hash output generated, and this hash output will be appended with the ASCII name of the content. Another one is hierarchical naming. Hierarchical naming is something similar to how we name the URLs. So, like we can have the names in a hierarchical manner, like maybe the content creator name, followed by maybe the creator have multiple channels, so XYZ. And then like we can actually like how we organize our file system as directories, we can similarly we can do this. Then within maybe have the creator have lot of videos, and within the video we can have one dot mpeg, we can have 2.mpeg, such a method. So hierarchical method. This method is actually in line with the routing compatibility also. Maybe we can use some kind of a longest prefix max and aggregation kind of techniques with hierarchical naming. The other naming is attribute based naming. So in attribute-based naming, it is like you name the content using its attribute, like the MPEG quality, the length, the quality, this type, and maybe the size, etc. The type of the content, whether it is a picture, JPEG, MPEG, and the length, how long the content is, what is the quality, 720p or 1024p, or based on that, we can based on the attributes, we can have the naming. But how we can ensure the uniqueness is also a question. So, given this naming convention, what we have to do is like do the match the following. So, if it is A, B, C, and 1, 2, and 3. Flat addressing matches to this one, hierarchical matches to this one, and attribute based matches here. So A2, 2, B2, 3, and C2, 1. Okay, so this is the matching. Now the last question. So correct, incorrect about security model. Model of the current TCP/IP network and information centric networking. Okay. TCP/IP protects the communication sorry. ICN protects the communication channel between a client and a server. ICN networks use data encryption and authentication at transport layer. ICN security model packet content names are associated with cryptographic primitives. Yeah. So the question is, which of the following sorry, it is not names, it is statements. Statements are incorrect about security model of current TCP/IP network and ICN. So TCP/IP protects the communication channel between a client and server using TLS that we know HTTPS work on like that. So yeah, TCP do that. TCP/IP do that. ICN protects the communication channel between a client and a server. No. ICN use data encryption and authentication at transport layer. No. In ICN security model, packet content and names are associated with strong cryptographic primitive. So they have a different, the content and names are associated with the cryptographic primitive. It's not at the transport layer. So A and D are correct, B and C are wrong. So the answer here will be B and C, which are incorrect statement is B and C. So with this, we're pretty much done with the questions. So Um, so I'm done for the session. If there are no more queries, then we can close the session. Yeah, thank you for joining. Bye. Have a nice day.